Good. All right, my name is Grant Adams, and this is a presentation on the gas turbine jet engine experiment that my group would be doing next week, but sadly it's not working, so all of this is theoretical. So a quick agenda before we get into the main point of the presentation. We're going to go over like a conceptual background of how a gas turbine jet engine works, go over the purpose of this experiment, some background on the Brayton cycle, and go into the theory, all the calculations and all that. A more in-depth look at how this machinery generates electricity. Then we'll go into the experimental setup, procedure phases, safety, and then references at the end. So this equipment right here is made by Turbojet. It's a jet engine, and it is used to create electricity. Ones like this are typically used in power plants when they're under really dire circumstances. They need a little extra electrical generation. So that's what the peaking is. It's like a surplus. They need a little more of an electrical boost. So that's when they kick these on. So for the main way of how a jet engine works, this is like the steps. So air enters the intake, it's compressed by a centrifugal compressor. It's mixed with fuel and combusted in a chamber, and that generates thrust, which then spins a power turbine and accelerates out the nozzle. So that creates the thrust that allows planes and things like that to fly. But in this case, the power turbine is going to be replaced by a freestanding turbine that will still move when the thrust is generated, but it will cause an electrical current to build up, and that electrical current is what we're going to be measuring to do all the analysis and stuff like that. So what is the purpose of this experiment? The main purpose is to gain an understanding of what this technology does, how it operates, and how we can use it in real-life applications like they do on the power plants. So we're going to conduct various procedures. There's a pre-startup, a startup, the actual operation, data gathering, and then shutdown of the gas turbine. We're going to perform system performance calculations for the steady state, steady flow constraints that this is pretty much facilitating. And lastly, we're going to use all these calculations and analysis to determine the optimal operational settings for the gas turbine engine, to calculate the power-specific fuel consumption during the production of the electricity. So a little background, the Brayton cycle is the basis for this experiment. And of course, we know the difference between an ideal and an actual cycle. So assuming an ideal cycle, which is what's pictured here on the left, there are basically four steps. There's an adiabatic compression, there's a constant pressure heating or addition of heat, adiabatic expansion, which is going to be in the turbine, and then the constant pressure relief of heat, cooling. Like I said, they are two different things. So in the actual cycle, it's not going to be 100% thermodynamically efficient. The turbine's going to be a little more work productive, whereas the turbine's going to be less work productive, whereas the compressor's going to be a little more work productive. So there's like some inconsistencies there. And then as I said, because it's not 100% efficient, it will be irreversible due to energy loss via heat, via sound, due to the inconsistencies in the work production as well. So that's something to keep in mind. So a little bit of the theory and the calculations that we'll be using. So all the way on the right, there's the well-known ones, the mass flow rate, volume flow rate. We've all heard of those. This specific experiment, we're going to be looking at like the work put in and the work put out, and then the work done on the free turbine. And then we're going to take all those, get a network, and calculate the efficiency and the intake Mach number down here, where it's volume over the speed of sound in the medium, which is down right there. So a little more in-depth look at how it actually generates electricity. They create electricity by spinning a turbine wheel, and that turbine wheel spins via a thermodynamic process, as I stated. This is a basic schematic of the electric alternator. It has two main parts, a stator and a rotor. As the name suggests, the stator stays stationary while the rotor moves inside. The rotor rotor is basically just some wire wrapped around an iron core, and from there it basically turns into an electromagnet whenever it's met with some electricity. The stator is just basically coils stationed around the rotor that captures the electrical current and produces an alternating current, and that's what's picked up by the sensors, and that's what that goal is to measure. So as we can see, this is an image of me operating that machinery. And then this bottom image is the master control panel. So you see here is the master switch, green light means on, red button means off, the power lever, the load lever. This is a start display. These three up here are just digital indicators for turbine temperature, speed, and then the engine speed as well. These are analog indicators for all the different pressures that we're going to be observing throughout the experiment. Then there's a voltage indicator, and then an overspeed warning light, which you don't want to turn on. But next, so there's a lot of procedures during this experiment. So I kind of just broke them up into phases. So the pre-start phase, you're just kind of putting everything to the base start level, where you want to just visually inspect the equipment, make sure all the levers work and that it's connected electrically. To start up the calibration phase, you're going to turn on the master switch, see that everything's lighting up, move the levers, see if they work or if they're obstructed. Then the actual operation, you're going to do everything, but this time press the start button, run the experiment, gather the data acquisition, and then for the shutdown phase, you're basically going to reset everything as you found it. So. And lastly, for safety, we got to wear proper PPE, so include shoes, safety goggles, and then for this one specifically, safety hearing protection, because it does get loud. We want to make sure we lock the wheels before operation, because it is mobile, it gets really loud, so ideally you would bring it outside. So when I inspect the equipment, make sure there's no cracks or oil spraying out. And it does happen, and have a fire extinguisher in handy in case the spraying oil catches on fire, but that's it.